Somewhere in the Western Australian desert, on a working sheep station that looks like every other working sheep station in this part of the country, there are fragments of rock that formed before the Earth had oceans, before it had a solid crust, before the moon was finished being born. They are sitting in the ground right now, on land that gets driven across by station workers moving stock, under a sky that looks identical to the sky over every other stretch of red country in this part of the state. They are not locked in a vault. They are not behind glass in a museum. They are in the dirt of a sheep station called Jack Hills, approximately 800 kilometers north of Perth, in a stretch of folded and weathered terrain that a traveler passing through would note as unremarkable and forget before they reached the next town. What is inside that terrain is the oldest material ever recovered from this planet. Not the oldest thing ever found in the solar system. Meteorites carry material that predates the Earth entirely. Not the oldest rock formation in the world, a distinction belonging to a greenstone formation in Canada, but the oldest known fragments of the Earth's own crust. The oldest known pieces of the surface of this specific planet. Material that formed 4.4 billion years ago, when the Earth itself was only 100 million years old and the conditions on its surface were so extreme that geologists named the entire era after the underworld, the Hadean. And it was found in Western Australia, on a sheep station, in crystals smaller than a grain of sand. If you are new here, this channel covers Australian history, science, and country that most people were never properly taught. Subscribe now and let me know in the comments below whether you had heard of Jack Hills before watching this video today. Let us start with what the crystals actually are. Because the material at the center of this story, before you add any of the extraordinary findings to it, is itself remarkable in ways that most accounts of the Jack Hills discovery do not fully explain. The crystals are zircon, zirconium silicate, a mineral that forms deep inside cooling magma when continental crust solidifies from molten rock, growing grain by grain as the temperature drops through the specific range at which its component atoms lock together into a crystal structure. Individual zircon crystals from Jack Hills are tiny, smaller than a grain of sand in most cases. Invisible to the naked eye unless you know what you are looking for and are looking very carefully. In the field, in the red dust of the Jack Hills terrain, they are entirely indistinguishable from ordinary sediment. The geologists who recover them do it by crushing samples of the host rock and sieving the crushed material through progressively finer meshes until the zircon grains are separated from everything else. It is patient, precise, unglamorous work. And what it produces, when it works, is crystals that have been sitting in the Australian desert since before anything we would recognize as Earth existed. The reason zircon survives when almost nothing else does is its durability. Zircon is chemically almost inert. It does not dissolve. It does not react with surrounding rock under normal conditions. It can be tumbled through river systems, buried under the pressure of kilometers of overlying rock, heated to temperatures that would melt most other minerals, and slowly return to the surface through tectonic movement across billions of years, all without losing the chemical record stored in its interior. That chemical record is the key to everything. When zircon forms, it incorporates trace amounts of uranium into its crystal structure and excludes lead almost entirely. Uranium decays into lead at a rate that is extremely well understood and extremely consistent. By measuring the ratio of uranium to lead inside a single zircon crystal with sufficient precision, geologists can calculate exactly how long ago that crystal formed. The more lead relative to uranium, the more time has passed since the crystal solidified. At Jack Hills, the oldest crystals have been accumulating lead from uranium decay for 4.4 billion years. That is the number. And arriving at that number with enough confidence to publish it required not just one measurement but decades of argument, technical innovation, and independent verification that the full story of Jack Hills cannot skip over. The first published dating of a Jack Hills zircon to this extraordinary age came in 2001, when a research team led by Simon Wilde at Curtin University in Perth reported a single crystal with an age exceeding 4.4 billion years. The paper appeared in the journal Nature and immediately became one of the most contested results in the recent history of geology. The skepticism was not unreasonable. The longer a zircon has been in the ground, the more opportunities there have been for the chemical record inside it to be disturbed. High temperatures, pressure changes, fluid movement through the surrounding rock, all of these can cause lead atoms to migrate within the crystal structure, producing ages that are older or younger than the true crystallization age. A claim of 4.4 billion years for a single crystal was extraordinary enough that the scientific community was not prepared to simply accept it without sustained scrutiny. That scrutiny lasted for more than a decade. The debate was largely resolved in 2014, when a team led by John Valley at the University of Wisconsin applied a technique called atom probe tomography to one of the oldest Jack Hill zircons. Atom probe tomography works by removing individual atoms from the surface of a sample one at a time and recording their mass, allowing researchers to map the position of specific atoms within the crystal structure with a precision that no previous technique could match. What Valley's team found was that the lead atoms within the crystal were not randomly distributed, as they would be if the crystal had been thermally disturbed and the lead had migrated through the structure. The lead atoms were clustered in specific locations within the crystal, consistent with the products of radioactive decay sitting exactly where they had accumulated since the crystal first formed. The crystal had not been disturbed. Its internal record was intact. The age was confirmed at 4.374 billion years, with an uncertainty of plus or minus 6 million years. For a measurement reaching back this far in time, that precision is extraordinary. Valley's published conclusion was that the chemical record inside the Jack Hill's zircons could be trusted. The decade of uncertainty was over. What Simon Wilde had reported in 2001 was real. Now let us talk about what the crystals have revealed. Because the confirmed age is only the beginning of what the Jack Hill's research has produced, and the findings that followed the dating confirmation are in some ways more surprising than the age itself. The trace element chemistry of the oldest Jack Hill's zircons encodes information about the conditions in which they formed. The specific combination of elements present in the crystal lattice, and the ratios in which they occur, are fingerprints of the type of magma from which the zircon crystallized and of the conditions under which that magma formed. What the trace element chemistry of the 4.4 billion-year-old zircons indicates is that they formed from magma similar in character to the granite and granodiorite magmas that form continental crust in the modern world. These types of magma require specific conditions to produce. They require the presence of water. They require crustal material that has been through a cycle of melting and differentiation that produces a composition distinct from the primitive mantle rock that characterized the earliest Earth. The implication is significant. If the Jack Hill's zircons formed from granite-like magma, and granite-like magma requires liquid water and a certain degree of crustal evolution to produce, then both liquid water and differentiated continental crust must have existed on Earth by 4.4 billion years ago. 100 million years after the moon-forming impact. 100 million years into the Hadean, the era named after the underworld for its presumed hellishness. The traditional picture of Hadean Earth was of a planet so thoroughly hostile that liquid water was essentially impossible. The surface was assumed to have been largely molten for much of the early Hadean, continuously bombarded by large impactors from the early solar system, and too hot and too unstable for stable liquid water to exist at the surface. The Jack Hill's zircons say that picture is incomplete. They say that by 4.4 billion years ago, the surface had cooled enough to support water and to produce the kind of magmatism that creates continental crust. They say that early Earth, at least in some places and at some times, may have been significantly more habitable than the Hadean label implies. Valley himself described the finding as evidence of a planet that looked considerably more like the world we know today than the hellish global furnace that dominated the scientific imagination of early Earth. This is a significant revision of how the beginning of this planet is understood. And then there is the carbon. In 2015, a separate research team reported the identification of a microscopic carbon inclusion inside a Jack Hill's zircon dated to approximately 4.1 billion years ago. The carbon was not the finding. Carbon is not unusual in geological materials. What made the finding significant was the specific ratio of carbon isotopes present in the inclusion. Different sources of carbon produce different ratios of carbon-12 to carbon-13. Biological processes preferentially incorporate the lighter carbon-12, producing a characteristic isotopic signature that geologists call biogenic carbon. The carbon inclusion in the 4.1 billion-year-old zircon had an isotopic ratio consistent with biogenic carbon. The research team, led by Elizabeth Bell at the University of California, Los Angeles, published the finding in the Proceedings of the National Academy of Sciences. They were explicit about what they were and were not claiming. The finding did not prove the existence of life at 4.1 billion years ago. A single microscopic carbon inclusion is not sufficient evidence for that conclusion. What it showed was that the possibility of life at this period in Earth history could not be excluded on the basis of the available evidence. If the biogenic interpretation of the carbon is correct, it would push back the earliest possible evidence for life on Earth by several 100 million years, to a period when the Earth was less than 500 million years old. It is a microscopic piece of carbon inside a crystal smaller than a grain of sand. And it may be the oldest evidence of life ever found anywhere. The researchers who reported the finding have continued to describe it with appropriate scientific caution. The biological interpretation has not been confirmed. It has not been refuted. It remains in the literature as a finding that requires further investigation to resolve. The same caution applies to a separate set of findings reported by researchers working with Curtin University and colleagues in Germany, who described microscopic diamond inclusions within some Jack Hills zircons dated to approximately 4 billion years old. The diamond findings have been treated with even greater caution than the carbon isotope result and remain contested within the broader research community. The caution that surrounds all of these findings is not a weakness in the Jack Hills research. It is a feature of it. The confirmed 4.4 billion year age of the zircons is credible precisely because it is the product of decades of rigorous skepticism, independent replication, and technical innovation applied to an extraordinary claim. The more speculative findings about carbon inclusions and potential biological signatures are treated cautiously because that is what the evidence warrants and what good science requires. Now let us talk about what the Jack Hills site represents in the broader context of Australian science. Because the discovery of the world's oldest known crustal material in Western Australia is not simply a record-breaking geological finding. It is a demonstration of something about the Australian continent that runs through every major scientific story that this landscape has produced. The ancient, stable surface of Australia preserves what other continents destroy. The same geological stability that preserves Australia's impact craters, that maintains the ancient basement rocks that geophysical surveys are revealing in increasing detail, that allows the survival of biological lineages in refugia that have been stable for millions of years, is the same stability that kept 4.4 billion year old zircon grains intact in the quartzite of the Jack Hills long enough for the dating techniques capable of measuring their age to be developed. The quartzite that hosts the zircons at Jack Hills is approximately 3 billion years old itself. The zircons it contains are significantly older. They were eroded from an even more ancient piece of continental crust, swept into what was then a river or beach environment, and deposited in the sediment that eventually became the quartzite of the Jack Hills. That original crust, the material from which the zircons crystallized 4.4 billion years ago, no longer exists anywhere on Earth in its original form. It has been destroyed by the geological processes that have reshaped the planet's surface across billions of years of subsequent history. But the zircons it produced survived, encased in younger rock, preserved by the durability of the mineral itself and by the stability of the ancient Australian surface that held them. The oldest fragments of this planet's crust survived because they ended up in Australia. That is not a coincidence. It is a property of the Australian geological environment that the scientific understanding of the continent has been progressively revealing across every discipline that has looked at it carefully. The Jack Hills research has not stopped. Geologists continue returning to the site. The catalog of documented zircon grains exceeds 100,000 individual crystals. Each field season produces new samples. Each new sample is another data point in the effort to understand what the surface of the early Earth actually looked like. Some findings confirm the existing picture. Others complicate it. The research community working on Jack Hills remains active, technically innovative, and genuinely uncertain about some of the most fundamental questions the site raises. That is what it looks like when science is working as it should. Not a closed case. A continuing investigation of the most extraordinary archive of early Earth history that has ever been found. Somewhere on a sheep station in the Western Australian desert, in rock that looks like every other rock in the surrounding country, the oldest known pieces of this planet are sitting in the ground right now. They formed before life, before oceans, before anything we would recognize as the world we live in. They survived everything that followed. They are still there. And the scientists who keep going back to find them are still working out what they have to tell us about where we came from. If this changed how you think about Australian science and the deep history of this planet,